Welcome everybody to this special seminar hosted by the IAU G2 and IAU G5 commissions. This is Sergio Simón Díaz. I'm staff researcher at the Instituto Astrofísica Canarias in Tenerife, Spain. And today I'm acting as the vice president of the IAU G2 Commission on Massive Stars and also as organizer of the official IAU G2 conference series. Normally, we have our online seminars on the last Thursday of the month, but today we selected a different date to differentiate this seminar from the rest. Normally, I do the introduction of the speakers myself, but for this special seminar today, I'm honored to give the floor to Lida Oskinova from Potsdam University in Germany, who is presently president of our commission. And also, before passing the baton to Lida, I would like to welcome Simon from Armagh Planetarium, UK, in UK, who is president of the IAU G5 Commission on Stellar and Planetary Atmospheres, and obviously our special guest today, Flor Broekgaarden. So whenever you want, Lida, the floor is yours.
Okay, so welcome everybody. I'm Lydia Oskinova. I'm president of IAU Commission on Massive Stars. And today we celebrate an event which unites all astronomers and which has paramount importance in the history of astrophysics and also in the history of International Astronomical Union. And we want today to recognize one of their key figures, a woman which was a defining figure in 20th century astrophysics. And who can better introduce Cecilia Payne-Gaposchkin than Flor Broekgaarden? So, Flor, thank you very much for agreeing giving the seminar today. Couple of words about Flor. So, Flor received a bachelor in Amsterdam in 2017, and after that she moved to Harvard, and where she received PhD in 2023. And her PhD was recognized by awarding Flor a Cecilia Payne-Gaposchkin Prize for Best PhD work. So this is a wonderful recognition of her achievements. And since very recent, my understanding, Flor is an assistant professor in University of California, San Diego. She's working on paleontology of black holes and studying how stars and black holes, stars died, and black holes were formed in times long past. So Flo is actively engaged with early career researchers. She had written resources which help young career researchers entering the field to navigate in stormy waters of academic life, and she provides support and guidance on this too. And Flo is also likes to explore California and hike and and I forgot to mention that Flo created some online tools which have some Dutch names, Stroopwafel, and maybe Flo at the end when there are questions, Flo can answer more about your own research. But for now, we would be very interested to hear about Cecilia and Flor. Thank you very much, and please go ahead with your presentation.
Yeah, thanks so much, and thanks everyone for joining. It's very just great to see a lot of people interested, and I hope this can really be kind of like just shared enthusiasm. Like, I love this thesis that we will discuss today by Cecilia Payne. It's so inspiring to me. But of course, I'm by no means an expert, right? I feel like within astrophysics, like probably many of you also here on Zoom know so much more about like stellar atmospheres, about like radiation. So I'm also really excited to have a discussion afterwards and also discuss other stories about Cecilia Payne. One thing I wanted to share is like some resources that I just put in the Zoom Slack, like the messages link. Because one small note is that there are actually amazing many resources online that tell more about like the story of Cecilia Payne. So like how she moved from like the UK to eventually like Harvard observatories, how she became like the first female professor there, and the first like the eventually like the chair of the Department of Astronomy and the first female chair of the Department of Astronomy. There's so much about that. There's definitely a lot of historians that can tell that story much better than me. And so what I wanted to focus on for this specific lecture is actually something a little bit different, which is instead of kind of summarizing her work or like writing these nice stories about her work, to actually look at her actual thesis. Because I find that in most of the like more historical notes, people summarize it or like maybe show one figure at most. But this thesis is actually really, really nice. So my plan is to do a really quick one-on-one, like what is this thesis about, to just go through it. So hopefully in about 30 minutes, you basically have read an entire PhD thesis, which is quite nice. And then we can kind of afterwards like comment on it and discuss it. And so you should be seeing my screen now. Yeah. So this is actually how the thesis starts. So you can download this, for instance, from ADS, and it was called like Stellar Atmospheres. And so it was a thesis written as part of getting your PhD degree at Harvard Observatory by Cecilia Payne. And so later on, she changed her name to Cecilia Payne-Gaposchkin. But this was still by Cecilia Payne. And so it was published by basically the observatory in 1925, which marks 100 years ago. But one thing that's also interesting is that actually the publication was somewhere between 1925 and like 1926. So basically it was like submitted around like January 1st, 1925. But it's almost like a year later that like things were edited, like editor word was added, and actually the book kind of got this stamp of the library that it like is now in the library. So I think this also highlight, right, that often research and even publications like take more than a year to really complete or be published. I think this is another example of even 100 years ago, it took, almost like 1.5 years to publish a thesis. So not uncommon, but I think it's great because it's, 100 years ago, so we can look back on this. Okay, so then this thesis, let's go through it. So start actually with the foreword, in this case written by like Shapley. And this foreword is pretty nice. It kind of sets the stage. I sometimes think like maybe today we should also have forewords being written by like thesis advisors or other people in the field. And basically what the editor here already wrote is basically it sets the stage. So 100 years ago, the main debate of this thesis is about is what are stars made of? Like what is the most abundant elements, for instance, in the stars? And it's a pretty interesting time to be studying this topic, because as we will discuss, there were a lot of new theories that allowed Cecilia Payne to eventually come to the conclusion that stars are mostly made of hydrogen and helium. And this was definitely like a very new idea at the time, as people often thought that the elements of stars and what stars are made of are very similar to, say, the Earth abundances. If you were to like put the Earth at like much hotter temperature, that's what you would create a stellar atmosphere. So let's go into it. So the thesis basically consists of 3 parts. The first part is mostly kind of like an introduction or like background. So it really sets the stage of like, these are the things that were needed for Cecilia Payne to do her groundbreaking research. Then it has like a part where it basically focuses on this theory of ionization. So things like the Saha equation that most of you might be familiar with or have heard of, that are so important for her work. And then actually in this last part is kind of where she applies now her findings to like real stars to make some groundbreaking results. So we'll go quickly over each of these parts. Okay. So this is part 1, laboratory astrophysics. So one thing that's also really cool about this thesis is that it combines many ideas from different fields and that were like so new in astrophysics, right? So even this idea that like we need to understand atoms, ionization, and really like chemistry or atomic models and quantum physics. And so one of the key ideas that were important at the time is that really at the time people were thinking about like these abundances of elements, for instance, in Earth. And so you have like your elements like hydrogen, helium, lithium, et cetera, et cetera, et cetera. which are represented by these different atomic weights, so just the mass of these elements. You have isotopes, which basically means, okay, the number of neutrons that you have in those atoms can change and can vary. And so you have different isotopes that were known at the time. And then this last column is basically what was known at the time, which is how common each of these elements are, like on Earth, so on terrestrial. And this is here represented as like a fraction of like atoms, so percentage of atoms that are, for instance, oxygen. So 54% of like all atoms on Earth were found to be like oxygen. So very, very abundant, right? And so this table is important because this kind of set the stage of like, okay, at the time, people really thought these are the abundances on Earth. Stars, most stars like the sun, they should be made of almost the same abundances, albeit at what we see is at a different temperature. And one thing is already really cool here, right, is that this really built forward on like a lot of the information known and studied before that really became public around these like 1922, 1921, when people were studying these atomic models and all these isotopes. Okay, oxygen is very abundant. The second thing that was really important for Cecilia Payne's work is really this new theory that also developed around 1920s by Bohr's model, like atomic model. And so really this notion that elements like hydrogen, helium, etc., have a number of electrons, and those electrons, go around the atom in these different energy levels, in these like different shells. So you can represent them a bit. And so we can characterize or try to describe and understand these atoms and their energy levels by these different electron orbits. So orbits that electrons go into. And electrons can also go from one orbit to another orbit, for instance, down or up, and release or absorb a photon. And so this is really, based on theory by like Bohr that Cecilia also cites from 1923, in which this like quantified element of atoms was known. All right, this is not so important. But the key idea that she used that was still somewhat new at the time, right? So now this is in every classic textbook, is really that if you have an electron, it can go down in the energy level, for instance, from energy level 1 or to energy level 2, or like go up between those energy levels, and it will produce or absorb a photon, but that specific energy level. So h times nu. Frequency, and h is here the Planck constant. And so there you have this quantified photon. So only specific photons of specific wavelengths or color can be absorbed or like re-emitted when these transitions take place. Okay, this is important because this is going to relate to lines that we see in spectra. And so there's more discussion of like all these different transitions that can take place, for instance, in like hydrogen. Okay. The other key important thing that was important for Cecilia's thesis is the theory of ionization, and specifically that like some elements can completely lose their electron if the temperature is hot enough, and so there's enough photons with high enough energy, then you can actually kick out your electron completely out of the atom and form an ion that, for instance, misses one or more of its electrons. And so also this theory is pretty new around that time, but really important, as we will see. And so what Cecilia does is mostly kind of give the background of all of these transitions, like where they're important. We can like skip over some of these out of interest of time. And then relate this to things like temperature. And so this is really where Cecilia starts building kind of a stellar atmosphere model for the sun, right? Where you basically assume that in this central source is like the sun, which is very hot and very intense. And then you have this atmosphere layer that consists of all these like atoms and different molecules. And photons will try to pass through the atmosphere outwards towards our eye. And what we see, or the result of that, is that some photons are being absorbed and some come through. So I have a picture here, very simplistic picture from a website that basically, if you were to look deeper into the sun's atmosphere, so very deep, it would be represented by a black body of a certain temperature. So really this whole rainbow spectrum. But then molecules and atoms in this atmosphere actually will absorb certain very specific photons of specific frequencies corresponding to these different energy levels and create these like dark absorption lines. And so inverse the spectrum from like bright to dark in those regions. And we'll see later on she refers to this as like reversing layer atmospheres. So it goes all the way back to like theories of radiative equilibrium by like Eddington and others, also all developed around this time. And specifically that there are certain temperatures for which ionization can take place. And already at the time, the thing that was new is that people were thinking and describing these concept like effective temperature, so that like a star atmosphere can be represented by an effective temperature, which basically represents the temperature or the spectrum that is emitted by the star is represented by a black body of that temperature. And so this represents this continuum that we're seeing from the sun. And so already at the time, people were trying to measure these temperatures for different spectra and different spectral classes of stars. But there is still a lot of disagreement between different methods. But people are trying to connect like stars, stellar atmospheres, these effective temperatures, optical depth with the stellar atmosphere. Okay, so what happens next? Yeah, and so this is really like where in chapter 3 and 2, where Cecilia goes into this background of like, okay, let's make a model for a star with a bright source, a photosphere that like basically creates the continuum, and then this like cooler reversing layer. Reversing because basically it can absorb some photons that try to travel through this atmosphere and make them instead these dark patches or dark absorption lines. Okay. Now, one thing that was really important around this time is to connect this to optical depth. So how far can photons travel before they are, for instance, absorbed? And also connect this to pressure, like the pressure in the atmosphere, which also relates to density. And this is going to say something about the amount of absorption that's taking place with this famous formula that I think a lot of people are using as well now. And so already then you can like kind of try to measure different stars, measure their temperature and like radius, and try to measure these pressures for these stars. And so this was at this time kind of the first time that people started doing this. Okay, let's continue a little bit onwards. A lot of this goes along like how do you measure line widths, like what can absorption lines tell us about the stellar atmosphere. It's super, super interesting, especially if you're studying like radiative transfer. But we're going to skip some of this for now out of the interest of time. Okay, and so then it really goes into like, so what creates these absorption lines for us? Oh, sorry, let me go back. Yeah, what creates these absorption lines? And so a little bit about like all the different atoms that are here, saturation. So like the more photons are being absorbed before they can escape the sun, it will be a stronger line, whether or not there is absorption or emission lines in these different spectra, etc. And then it mostly goes, so again, this is like all the introduction, right, for all the like actual work that is about to come. But it basically goes into all these different elements, discussing them in much detail. This is super fun to read, actually. But all these different elements that people think are present in stars, and for instance, the evidence that we have for their presence. So it talks a little bit about like Wolf-Rayet stars and like other stars, oxygen, and so on. Okay, we'll scroll through it. Super interesting. Okay, so that is all the background, right? So the background is we are setting the stage where basically we understand and are thinking a little bit about temperatures of stars. We have these like simplified models for stellar atmospheres where you have a star atmosphere, you have different elements like abundances like in the stellar atmosphere. And now we'd like to actually model them. And so there are some theories about how pressure relates to like optical depth and to like density and like line intensity or width. But how do we actually go on and do this? And so for that, the most important part of Cecilia Payne's work was to really think about ionization theory, which was based on like size equations and earlier theories from like Milne. And so for this, let's go into more depth. But the basic idea is that, okay, you have all these ions, and these different atoms have like specific energies for which they can be ionized. So how much energy photons need to be in order to actually ionize these atoms. And this is going to change per element that you're discussing. And actually, there were a lot of elements for which this was not known at the time, what this energy actually might be. They still had to do more lab experiments to determine it. And of course, those ionization energies are going to correspond to the wavelength of photons that is required. Okay. So the thing that was really important was also this work by Milne then, and then later on by Saha, which basically then determines that ionization is dependent on temperature, and gave us this equation that tells us the fraction. So X here is the number of atoms that are ionized. So basically the relative fraction of ionization is equal to, and here's the, oh, let me go back. Guess I shouldn't do that too much. Oh. Let me go back to the Sa equation. So here's like the key equation that was completely new at the time, which basically says that the fraction of atoms that are ionized in your atmosphere can be calculated by this equation, where basically this B as a function of T is like your partition function. So the distribution of atomic states of your elements. This is usually kind of like a constant, or we can derive it. But then most importantly, it's this factor, which is a function of the temperature, and then this e to the power minus psi, so this is the ionization potential, so this energy that it requires to ionize it, divided by the Boltzmann constant, and then the temperature. And so this was really, really unique. And the most important thing to take away from this is that there's basically two regimes for this equation. So at very low temperatures, this value, e to the power minus psi over kt, is going to be very small. And so it means that this 1 minus x is going to be very similar to 1. Like basically this term just becomes like b over b, and this is very small. And so it means that x becomes 0. So basically, none of the atoms in your atmosphere or in the gas that you're considering are being ionized, They're all in their neutral or like less ionized stage. Whereas at high temperatures, or very high values of T, this e to the power minus psi over kt actually becomes very large. And so this 1 minus x actually goes towards 0 in this equation. So this becomes very large. And so this whole term becomes 0, which means that x basically becomes like goes slowly to 1. And basically the entire gas becomes like ionized. And so this equation tells you now for any temperature what fraction of your atoms are ionized or are not ionized. And so there's a critical temperature where basically you go from like one state, like everything unionized, to the other state of like everything is not ionized or is ionized, sorry. And so this looks something like this for different elements, where basically here in the top, this is in the, so it's actually fun to know for the younger people among us that like, you know, back at the time, we didn't have nice Python packages that do all the like plotting for you. So actually often they didn't have like axes. This is why I like wrote here myself kind of the units and like what the labels are of the axis, because it wasn't so easy to put this into these theses. But basically what this shows is on the y-axis, this like the logarithmic of like 1 minus x. And so it means that if you're close to 0, so basically you're 10 to the power 0 or 1, you're in this regime where everything is ionized. Sorry, everything is not ionized. Everything is, for instance, like more neutral. So x is very small. Whereas if you're very low here on the y-axis, you're basically going through this regime where 1 minus x becomes like 0, like goes towards 0. And so slowly all your atoms are being ionized. And so this makes sense, right? Because on the x-axis, it shows temperature. And so what we're seeing is that as you go to higher and higher temperature, more of your atoms become ionized, like a larger fraction of all your atoms become ionized. As there's more photons available with higher temperature or higher energy, sorry, I should say, that can ionize all those elements. And so this is going to depend on these different elements. So it's not the same for each element at which temperature this transition happens and what this fraction is going to be. And so some elements have like a higher ionization temperature than others. This is really key. Temperature is in Kelvin and then times 1,000. Okay, so then the important figure is this figure, and it's a little bit confusing figure, but it's an example for absorption lines, what this might look like. And so what it shows again on the y-axis is the logarithmic of 1 minus x. So again, in the top, you're kind of not, you haven't ionized another electron, whereas at the, at the top, you're like more neutral, whereas in the bottom, you're like more ionized. And so it goes as temperatures. Now, this example is shown for magnesium 2. So magnesium that already has lost 1 electron. And it's basically asking like, okay, we're interested in a specific line, in this case, 4481, that happens when you can basically excite like a higher, already excited state of magnesium 2, when you can excite the electron even more, then this magnesium 2 can actually absorb this photon of this exact frequency. And the question that Cecilia basically asked, like why she made this plot, is to ask, okay, when is this line, this absorption, the strongest? So when can we expect to see most of this absorption happening? And so when we look at this star's atmosphere, we can actually see the strongest absorption lines. And then there's 2 key effects that play a role. So first of all, in this case, we're interested in magnesium 2 that can then excite an electron and thereby absorb that photon of that specific frequency of this specific line. So this is a very, very specific like transition for this specific line that's creating an absorption line. Now, the fraction of magnesium 2 is going to decrease as a function of temperature. And so this is because magnesium 2 is basically being ionized to magnesium 3. So it's losing another electron, which means compared to the overall population, this is going down, and you have less and less magnesium 2 that is slowly converted and being ionized into magnesium 3. And so as a function of temperature, you're going to see less and less and less like chance of having this magnesium 2 that you need to absorb this photon. On the other side, in order to absorb a photon, you want not just magnesium 2, but you want magnesium 2 in an excited state that can then transition this electron to an even higher state that is specific of this transition for this specific line of 4481. And so what you see here, this dotted line, is that if you're at too low temperature, then, maybe there's there's some magnesium 2, but it's not enough of them are in an excited state that you can have this specific transition that corresponds to this line. And so only at higher and higher temperatures are there going to be more and more magnesium 2 in this excited state, so you can have this absorption of this specific photon. And so if you combine these two and multiply them, you get this solid line, which now tells you how many photons corresponding to the energy of this specific line are being absorbed, like before it or when we, and so how strong the absorption line is going to be when we observe it in our telescope on the Earth. And so what you see is that this is basically a curve that goes up. So the more magnesium 2 there is, the better it is. But then it also goes down again because at some point there's just too much of the magnesium 2 has been ionized to magnesium 3. And so you have this peak in this graph where basically there's a temperature at which most photons are being absorbed. And so you have the strongest line intensity. So most photons are absorbed here, fewer here of this specific line. And so you're going to expect that your line is the strongest around this temperature rather than these other temperatures. And so this is a really cool insight, like to really think of ionization and absorption lines as a function of temperature and how there might be a specific temperature at which these absorption lines peak. Okay, that was really nice because basically you can design these kind of like peaks of these lines for like any atom or any molecule or any line, like any frequency of a line that you're thinking of. And so that's kind of what Cecilia discusses here, this like general shape of these lines that always peak at a certain temperature. And this is going to be different for different elements. And so again, you can also relate it back again to like pressure using these equations. But the most important graph is going to be here. So, so you find it? Yes. This is basically the graph that now tells you again as a function of temperature. And this is the fractional concentration of these different lines and the observed line intensity. And so basically, as you go here on the x-axis, it shows all these spectral classes of different stars that correspond to different temperatures in the atmosphere, these like effective temperatures. And basically what Cecilia showed is that like the observed intensity of the lines that people were seeing already in these spectra exactly correspond to these like theories that she could derive with the fractional presence, like how fractional abundance of these elements in the atmosphere. So basically what she connected is like, okay, because there are these temperature, to really connect it back that this has to do with the amount of ionized elements in this, like the presence of that, but that it really has this peak temperature for which the line is the strongest that relates to this, like, okay, how many of these elements are there and how many are in an excited state that correspond to these specific lines. And so you can, it's almost like a theory and observation plot that perfectly align and that really gave her the confidence that we can like relate spectral intensity, so the intensity of lines, back to the concentration of those elements in the atmosphere, which is really cool. And so here Saha was really important. Okay, so then she did this for a bunch of stars. And one of the things that, for instance, she can actually derive is, first of all, just the temperatures of stars. And so she really made this model of like, okay, when we see stars with different elements and we see different absorption lines, we can now invert it and actually trace back what the temperature, like the effective temperature of those stellar atmospheres are. And so she made this table, how different stellar classes correspond to like different temperatures, and really like emphasizing this theory that the reasons why we see these different spectral classes, so stars with very different absorption lines that peak in different elements, that the key thing there that connects this is really this effective temperature of the atmosphere that then sets which elements are creating absorption lines and how much they're ionized, for instance. And one thing that's really cool is that so this was derived 100 years ago, these temperature scales are actually super, super close still to the ones that, for instance, Wikipedia now lists for the stellar types of stars, so OB, A, F, G, K, M, etc. Just showing that like already at the time, this was like a really, really good estimate. Of course, our observations have improved a little bit since then. So especially for the more extreme stars on this end, the numbers have adjusted a little bit, but still very, very close to these numbers, which I think is very cool. Okay. Now, she didn't just stop there, right? So that would be a pretty amazing thesis to just, not just, but like to really connect stellar atmospheres with the element abundances in the atmosphere, with the temperatures of the stars and how all of these are connected. And so how we can confirm what the temperatures of these stellar atmospheres are based on the different absorption lines that we see. That's already a pretty wild thesis, in my opinion. But Cecilia actually took it another step further, which is super, super interesting. And basically decided to take it a step further by basically flipping the Staha equation. And so basically here is that like, okay, as you increase temperature, as we saw, the line becomes stronger and then weaker eventually. And so you can also think of like a maximum temperature for which the line still exists, like an absorption line is still present. And so that must be where almost all of your atoms are like ionized. Because then if you increase it a little bit more, then all of them are ionized, and so there can be no more absorption, because you're missing your element that actually you need for absorption because it lost like an electron, and so it behaves very differently. And so because of that, it means that there's this maximum temperature for which basically you can still create an absorption line. And so these species are still present. And then she assumed that the amount of these atoms that need to be present to create an absorption line is basically the same among all species. So you can kind of think of it as like, okay, if you have 100 of those atoms, say magnesium-2, still in your atmosphere, 100 is enough to like absorb 100 photons. And so that will create an absorption line compared to the intensity. This is a huge assumption, but that's basically what she assumed, that basically this total number that you need for a minimum, like the minimum number you need for creation of an absorption line is the same across many, many species. And when you do that, this becomes awesome because basically you can define this fraction of species, like atoms that can are able to absorb the specific photon that corresponds to a line over all atoms of that species. But then if this one is fixed at that temperature, so at this maximum temperature where you just see your absorption line, if that always corresponds to like the same 100 elements that must be there, like 100 magnesium-2 atoms, then basically this is fixed. And so you can calculate just the total fraction or total number of like atoms present, as long as you do it as a ratio of other species. And so the nice thing about this is that you can use this to actually calculate the relative abundances of elements. And so this was really, really new, that now there is a method with these assumptions and caveats, comes with lots of assumption and caveats, that you can actually get the actual abundances of a species in the atmosphere. So how much hydrogen or helium or oxygen is there in this stellar atmosphere? Okay, so let's quickly look at the results. I'll scroll through this. Yeah, so this goes a little bit more into the theory. Yeah, and that like this photosphere, so like where are these atoms? But the main thing, and it comes with some caveats, but the main table is this one. Right now she shows, using all these theories, the abundances of these elements. And the main thing that she's finding is that actually this helium, for instance, so this is in log space, so 10 to the power 8, 10 to the power 11, 10 to the power 12. But especially that this helium is like very, very abundant in stellar atmosphere. Like the one you had from Earth is much, much lower than here, where it's like 10 to the 12, 10 to the 8.3, which is crazy. And also that these elements like helium are much, much more abundant than all these other elements that people thought were very abundant. So things like iron. So people used to think that like stellar atmospheres had a lot of iron, like equal amount as say the Earth, just because the iron lines were so strong in these abundance patterns, and because on Earth it's so common. But this really showed that helium is like a really important element in stars. And so that stars are mostly made of hydrogen and helium and not all these other elements like on Earth. And so it says, for instance, the lighter elements in stellar atmospheres, like they're very abundant, and it's a striking aspect of the results. And it's different from the composition of the Earth surface. Now, one thing that's funny is that, of course, at the time, this was like a really non-conventional idea. So also many people around her actually told her like, oh, this cannot be true. Like it must be that your thesis, like your results are wrong. And so one thing that Cecilia also does here is to really discuss like, oh, what are some ways that this can be wrong? And so for instance, like maybe in the sun's atmosphere, particles actually sink, or like it doesn't represent these abundances, and so all these like other reasons like why her results actually might not be true. And one thing that's probably a lot of you know is that also Cecilia was actually encouraged to kind of put more uncertainty on her findings. So, for instance, she wrote these things like, although hydrogen and helium are manifestly very abundant in stellar atmospheres, the actual values derived from the estimates of marginal appearance are regarded as spurious. So basically here she like in all this text, she's saying like, okay, I found that helium and hydrogen are the main elements, but there must be something wrong because, we know from past theory that this is not the case. And we're adding all this, that there's some inaccuracy and uncertainty. And so actually it goes in many chapters, like in detail, like the possible uncertainties in her theory. And she also like ends with this, like the outstanding discrepancies between the astrophysical and terrestrial abundances are shown indeed for hydrogen and helium specifically. And that the enormous abundance derived for these elements in stellar atmosphere, so these high abundances that we're finding for stellar atmospheres, is almost certainly not real. That's what she stated at the time in her thesis, right? So she was like, okay, this must be a mistake in this thesis. And of course, now we know it wasn't a mistake, and it actually turned out to be that they are the most common one. Oh. Yeah, and so in the rest of her thesis, I just want to show you the rest. She just goes into like more future prospect of like what this could mean, and like why this is so important, and of course like all the different citations and so on. But the thing I mostly wanted to highlight, let's see if I can stop sharing screen, and I see this time. But the thing I most wanted to highlight that this is kind of amazing, right? That she used pretty basic astrophysics to basically, Bohr's model, ionization theory, people who were started making these models for stellar atmospheres, these like Draper catalogs where people had really observed in detail absorption lines and stellar spectra of different models, combine this to then think about this like, okay, the spectral lines and strength of spectral lines and absorption lines changes as a function of temperature and changes for different species of temperature using the Saha equations, and then reversing this to actually being able to derive things like the temperature of stars, like how the different absorption lines that we see connect to different effective temperatures of stars. And then later also like these abundances of species. And I think it's so interesting and inspiring that she found that actually our stars are mostly made of hydrogen and helium, different than that we thought. And that although her advisors and many of her mentors really told her like, okay, this is probably wrong, you should put all this uncertainty, that she still put in her thesis like the actual results, and mostly that like, okay, there are uncertainties, but the results are the results, and this is what we found. And so this is actually how later on people, then of course did more and more observations and like developed more theory and found that actually stars are mostly made of hydrogen and helium. And so for maybe my peers and other young astronomers, like when I read this thesis, there's maybe three things that it inspires me for, which is first of all that we're standing really on the shoulders of giants, right? So she really had to use all these theories from people before her that were developed around the time to come up with this new theory. And so I don't know, maybe it's a good motivation to sometimes pick up that electromagnetic book or read papers and think about like maybe in someday you'll use some of these results. But also that we should keep on studying topics and results beyond those that are conventionally accepted because they might actually be really important and hold on to be true. And I think a little bit inspirational message is just the power of uncertainty, right? So you can do all this work, and even if there's all this pressure of maybe it might not be right or exact, to try to state and understand what the uncertainty in your model is, and state that clearly in your thesis so that you can still keep your results for, first of all, which might actually turn out to be true, but also to give like the fullest representation of astrophysics. Yeah. So thank you for listening, and yeah, let me know if you have things to add or other fun things you liked about it.
Thank you very much, Flor. I find it very, very interesting the way you have decided to deliver this talk in the way just going through the thesis, because this shows us also that, as you were saying, we don't need very fancy PowerPoint presentation to present interesting results. But this is just what is inside and the way you tell the story, you know. And then in this regards, I decide to do an exercise myself. So I was listening to you as if I were 100 years ago and not today. And even it's the same things that I listened when I was in my master lectures. It's a completely different way. So I was amazed with all the things you were saying. So I think it's also the way we see or listen to the things that people are telling us. So thank you very much for this. And the first thing I want to do is to give the opportunity to Simon to say a few words, like complementing what Lida was saying, since you are the president of the Commission on Stellar Atmospheres. So anything you want to add here?
Well, thank you very much, Sergio, and thank you very much indeed for your presentation. I'd just like to say something on behalf of Commission G5, Stellar and Planetary Atmospheres, which owes probably its entire existence to Cecilia originally, and what you've done this afternoon is just to demonstrate a little bit of Cecilia's legacy to us. I've been struck for the whole of this year. I've been reflecting on her work, and it goes back, I suppose, to when I started my PhD. My first term, my first task was to write a code for a stellar atmosphere, a very simple stellar atmosphere at that point. And very sadly, during that term, it was the same term that Cecilia passed away. And I remember our professor coming into the room and making a tribute to her at that time. It was a name that meant nothing to me as a young, just starting PhD student. But you look back now and you realize how naive I was then. And another thing that struck me during the year is there's a close connection between Armagh and Harvard. Harlow Shapley was acting director here, and one of our directors through the middle of the 20th century did his PhD at Harvard. And in fact, the copy of Cecilia's PhD thesis that we have here in our library belonged to Priscilla Fairfield, who is Bart Bock's later wife, but was a colleague of Cecilia's, and it has Priscilla's annotations in it, and it's fascinating to read some of those things. And what you get by looking at some of these old PhDs and other people's annotations is fantastic. But yeah, so what you've done this afternoon is to give us a beautiful pedagogical review of the thesis, and it's really nice for the nearly over 140 people who were attending this afternoon, I think, to have heard that, and I think some of them, I imagine some of them will have seen some of it for the first time, and I'm sure that you'll have inspired many of us in doing that. And you haven't left anything out as far as I can see. Temperatures of stars, abundances of elements, and the controversy surrounding it. These are landmarks. So on behalf of myself, and I hope on behalf of everyone who's been listening, thank you very much indeed.
Okay, thank you very much, Simon. So now it's time for questions. Just telling things you want to share, comments by people. So we are more than 100. So I'm sure there's people here who wants to share their yeah, opinions on this or memories. Anything you want to start? Anybody here? Don't be shy.
No, so can you hear me?
Yes?
Well, I think we should also reflect on their time and specific circumstance in which a woman was starting to entering the physics and astrophysics in particular. So Cecilia education started at Cambridge in a college which was reserved only for women, and then she moved to the US, where she was apparently very welcome and supported by the Shapley in Harvard, and of course with long tradition of women computers in Harvard. So it is all plays very well together. And I think that after Cecilia results, the role of women in astrophysics is not negotiable anymore. That was also a very fundamental statement made exactly 100 years ago.
Sergio, you're muted.
Okay, thank you. I was saying Karina, but since you are already unmuted, Annalisa, you can directly go yourself, and then we'll go for Karina.
Okay, thanks. Annalisa De Chia, astronomer at TISO. Thank you very much, Flor, for the beautiful explanation of Cecilia's thesis. This point of when she says it's almost certainly not real, did you get whether it was really her that was convinced, or was it a reaction from Russell and Shapley not being convinced about it and her, kind of being obedient? Because she doesn't say much in her biography either.
Yeah, no, that's a good question. So I don't know. And I would also really recommend like also for the story about like, how was it for her? How did she get inspired from lecturers to come to the US to do astronomy as a one of the few women astronomers? Like to really there's this great like Zoom recording by Donovan Moore who talks about the historical aspect also in this debate. So from the thesis, I think it was a bit of both. So definitely influenced, right? So like the historians also would tell me that she wasn't even, they didn't let her publish the thesis without those extra notes on uncertainty. So like I just imagine that like she handed in the thesis and then there were like corrections, add some information about uncertainties. I do think that thesis, like also these theories, right, allow for these uncertainties. So some of the uncertainties she talks about are like real uncertainties. Like now we know, like, okay, the numbers ended up being very similar, but there were uncertainties about like, for instance, assumptions like are spectral lines always created, or can you assume the same abundances take place? Like stellar atmosphere are very complex. So I think some of those were like definitely like the way that she writes about it is I would, they're very serious uncertainties, and so they could affect the results. But yeah, I think it's a bit of a combination of both. Yeah, great question.
Okay, if today was already a special day for many people, I think it's going to be even more special because we have here with us Cecilia, who is the granddaughter of Cecilia, and he is telling me that she can comment directly on this issue. So whenever you want, Cecilia, thank you for joining us.
Hi, thank you, Sergio. I'm Cecilia Gaposchkin, Cecilia the Younger. I'm actually a historian. I teach at Dartmouth College. I'm a medieval historian. And Rudy Lindner, an old advisor of mine, and I believe a student of Cecilia Gaposchkin's, was sort of the link, sent me information about this. I don't understand most of the science. I have my own talk on her, which is much more historical and speaks to many of the issues. I can tell you just, so she died when I was 9. I have very clear grandmotherly memories of her. So I've gotten to know her mostly through her own writings, her autobiography, and my father's memories of her, and that was a very important relationship. And I will say that to this issue, two things about the issue of what she felt in her thesis. In her own autobiography, she talks specifically about it retrospectively, and later in her autobiography, she has sort of lessons to the young, yet lessons to young astronomers. One of which is, if you are sure of your facts, you should stick to your guns, which is what I think she actually did in her own way, um, by publishing what she did and then pursuing it. I know it was painful for her, and I know it continued to be painful for her. Well, I know I'm told from my father, who was himself a scientist, and worked at the Smithsonian in Cambridge, near where we grew up, that that was actually quite painful for her. But she was, as I understand it, and this is where the science, I don't understand the science, but what I do understand is that she was working with some very new theories, and very new findings themselves, which had still to be uh, tested and approved. And so there are all sorts of ways where things could have gone wrong. And so she was certain of her own work, but had to, I think, um, allow for the possibilities that some of that was not on tested foundations. I think the great, um, historically, as I understand it, the great frustration was not so much Shapley, but oh, who's the guy at Princeton? Help me out. Sorry?
Russell.
Yes, yeah. His not rather, yeah. I'm forgetting my details, but his refusal, or his anxiety, his lack of support initially, and then his subsequent fairly recent adoption or findings, maybe through slightly different methods of the same findings that he got credit for, what was really her most spectacular sort of headline discovery. You can tell me whether that's correct or not, but
No,
that's my understanding
absolutely.
of it.
Yeah, thank you for adding that. And that's also to say, like, it took a really long time before she still got credit for her work, right? So indeed, like Russell and others got a lot of credit later on for like confirming it. Um, and even at Harvard, like for a long time, I think she got really low pay, or like, it was hard to be a female scientist at that time, and took a really long
It's
time for her to become like a professor. Like basically, like
so it wasn't.
the director of Harvard had to resign, right? And finally, there was like a director, like the president of Harvard, that like
Yeah,
allowed women to do.
the story as she tells it in her autobiography is that, I mean, she was essentially just a staff, um, a staff scientist working, and it was only when Donald Menzel, uh, who was from Princeton and who Shapley, again, this is in her memories of it, which has sort of a nostalgia to it in her writing, that Shapley had encouraged a kind of rivalry between the two of them. I remember Donald Menzel as a kid. I mean, they were very good friends later in life. When he arrived and he was given the position of director of the observatory, he looked at the numbers and he was appalled at what she was making, and pretty much overnight doubled her salary. Again, Rudy Lindner, Professor Lindner, was writing to me a bit about this the other night. Apparently, in his papers, he did even documents that he did even more than this. Then she was at that point given she had been teaching in an unofficial capacity, kind of as a, adjunct instructor, and she was given a formal faculty position at Harvard. The astronomy department, Shapley had basically created the astronomy department to have a department that could issue her a PhD, which is why her PhD is the first PhD from Harvard's Department of Astronomy. Once she was given a full faculty position, she was run through tenure and all that, and she was made full professor. Um, she was in her 50s at that point. She was 52. And it's interesting looking at her output. it the nature of her scholarship changes because she becomes suddenly saddled with all these administrative duties. She becomes chair of the department, so she begins writing some sort of more synthetic works like the Stars in the Making and some of her textbook, and a great stylist, which she credited for being, well, she credited it for being the editor of the Astronomical series. It's probably for her classical education, you know, all that Ovid and Homer that she read as a kid, I think, more than anything. But uh, anyway, so that at that point she's elevated.
Yeah, and that's great. And I don't know if you how much you know about this story, but I also heard this story that like so almost only 100 years later, like 90 years later, in like 2000 something, Harvard finally made like had a portrait of her made and like put in the faculty
Yeah,
room. And like the portrait, I'll post like a link for people. It is like amazing, inspiring portrait where she kind of like looks up and is like almost like like I'm not bothered
yeah,
by, I'm just
the
Cecilia. And it was like rumored that like actually they hang the portrait in a way that she actually kind of like looks up like over the previous like president for like
right.
here I
So
am and no one is bringing me down, which I think is like so
yeah,
amazing and inspiring.
it's a really beautiful portrait. It's again, I'm forgetting the name of the artist. It will be on the website. Um, she based it, or she took inspiration from one of Vermeer's portrait of the astronomer, which I think is a lovely tribute. In For those of you who have spent any time at Harvard, there's in University Hall they have all the great portraits of the great men, and there was only other one portrait of a woman, and I have to say this was a medievalist. So I'm a medieval historian. Helen Maud Cam is the other first woman professor at Harvard. So I take sort of delight in the fact that those are the two images. At the time, it was critiqued as a kind of affirmative action move on Harvard's part to include, like, we need a woman in the hall. Probably some truth to that. Um, and actually, I haven't been lately. I don't know whether they've added some more, hopefully, women to that. Um, but people are more, I mean, I have to say, I get a lot of email about her, a lot of inquiries. I'm in touch with a lot of people who are doing musical projects or children's books or other items like that. I'm sort of, obviously, because I was given her name and am findable, I think, on the web because I have a university post, a lot of that's get directed, and she's getting more and more attention. There's a recent film made about her and things like that. So it's lovely to see the scientific recognition for the basis of the science more than her. Um, I mean, I think, and I think this, I hope this would be her agenda as much as mine. I think it's good that she's being celebrated for her science and not for her womanhood, if that makes sense. What's important is the nature of her science, not the fact that she was a woman, which is historically interesting, but not the main point.
Sure, I fully agree. So thank you very much, Cecilia. It's amazing to have you work here. Karina Mauko wanted to say something before. Maybe you want to still.
Yeah, no, thank you. Thank you for the talk and everything. I really enjoyed it. No, my question was exactly the same as the one that Annalise asked. So it was already answered. So thank you.
Okay, perfect. Any other comment here? Okay, so maybe then we can stop. I'm sure people after watching this talk and the conversation we had, especially since this will be recorded and put in YouTube, so many other people will have the chance to watch it, and I'm sure there will be more conversation, and Cecilia will be better known, and I think this is especially important for the new generation. No? That's yeah. Okay, so then from my side, thank you very much again, Flor, for accepting this big challenge that we put you. And I hope you also enjoyed delivering this talk. And on behalf of the two commission, yeah, again, thank you very much.
Thank you. Bye.
Ciao, ciao.
Thank you.